morning. Welcome to the Week 11 Math 2413 review. This one we'll be going over a little bit of practice with L'Hopital's along with some graph sketching, and then we'll be focusing in on some optimization problems as well as some intro to antiderivatives. So we'll start out with just a really quick review of L'Hopital's. And if you'll remember, L'Hopital's rule says if we have the limit as x goes to some point of f of x divided by g of x, and we get an indeterminate form, such as 0 over 0 or infinity over infinity, well then we can say that the limit as x approaches a of f of x over g of x is equivalent to the limit as x goes to a of the derivative of f of x over the derivative of g of x. So I'm actually not going to do an example problem. I did a few example problems last week. I'll just give you guys a couple of practice problems, and then we can work those out afterwards, after you get a chance to fill it out. So the first one, the limit as x goes to 0 of e to the x minus 1 over the sine of x. This one is fairly straightforward. And our second one will be the limit as x goes to 0 from the positive side of x to the x power. And I'll give you guys a couple of minutes to work through those. Saying they're both equal to 1. All right, let's go over these. The first one, well, when we plug in our 0, we would get e to the 0 as 1 minus 1 is 0 over sine of 0 is 0. So we just apply L'Hopital's. And the derivative of the top is e to the x. And the derivative of the bottom is cosine of x. We plug in 0, we get 1. Plug in 0 for cosine, and we also get 1, which is 1. So our first one is 1. Our second one, we don't really have in the form of L'Hopital's. We do, however, still get an indeterminate form when we just plug in 0 of 0 over to 0 power. So we can't really just plug in our limit that way. Let's say we have the number some L, and that L is going to be equal to our limit respects to the x power. Well, if we take the natural log of each side, this tells us that we now have the limit as x goes to 0 from the positive side, the natural log of x to the x, which is equal to the limit as x goes to 0 from the positive side of x times the natural log of x. Now, we're still getting an indeterminate form here, but it's not quite in the form that we can use L'Hopital's for. We need it in the fractional form of f of x over g of x. So I'm going to rewrite this by moving my x to the denominator, like so. Well, now when I plug in 0, I get the natural log of 0 from the right is negative infinity, over 1 over 0 is positive infinity. This is still an indeterminate form. So I can apply L'Hopital's here. The derivative of the top is 1 over x, and the derivative of the bottom is negative 1 over x squared. So I cancel, and I get the limit as x goes to 0 from the positive side of negative x, which is, of course, 0. I'm not quite done, though, because I took the natural log of each side. So I take the natural log of some limit L, and I know that's equal to 0. So to cancel it, I raise both sides to the power. So now I have that L is equal to 0. So L is equal to 1. That's just a brief review of L'Hopital's. Since we mostly covered it last week, I'm not going to spend any more time on it. Of course, feel free to have questions if you do. Feel free to ask questions if you have. If there are no questions, though, we will move on to graph sketching, which we also talked about last week. So we'll be doing just a bit more review of this. So again, I'm actually not going to give you an example problem, but rather just jump straight into a practice problem, which I'll then work out in detail so you can see how it's done if you have trouble. So our first one, I'm just going to have you give me a detailed graph of y is equal to x cubed plus 2x squared minus 4x minus 8. And what I want you to include are intercepts, both x and y. I also want to know where the maximums and minimums are. So every maximum and every minimum should be on the graph, as well as the intervals of concavity. These should also be clear from the graph. And I'll give you guys a few minutes to work through sketching that graph. Good luck. So I want you to label every single extrema. So if it's an absolute extrema, go ahead and label it. If it's a local extrema, also find that and label it on the graph. Basically, give me as detailed of a sketch as you can. Mm-hmm. All right, let's go over this one. So let's start out by finding the intercepts. So the points where y is equal to 0 and where x is equal to 0. The y-intercept is usually pretty easy to find. All we do is we plug in 0 for x, and we clearly see that we have a y-intercept at the point 0, negative 8. So I'm going to go ahead and plot that right there. Similarly, if we wanted to find our x-intercepts, we would set y equal to 0. So then we have 0 is equal to x cubed plus 2x squared minus 4x minus 8. Now we just simply need to factor this. There are a couple of different ways we can. The way I'm going to go with, though, is factoring out an x squared from the first term leaves me with x plus 2. Factoring out negative 4 from the second term also leaves me with x plus 2. So then if I factor out an x plus 2 from both of these terms, I'm left with x squared minus 4, which I can then factor into x plus 2 times x minus 2 times x plus 2, which is, of course, equal to x plus 2 squared times x minus 2. So then clearly I can see that my x-intercepts are going to be at 2 points, at negative 2, 0, and also at 2, 0. So I'll go ahead and plot those as well. I'm going to move it further out. Oops. Okay. So that's it for my intercepts. Now I need to find my maximums and my minimums. To find my maximums and my minimums, I need to use the derivative. So my derivative is 3x squared minus 4x, plus 4x minus 4. If I wanted to find out where this is equivalent to 0, I don't want to bother factoring, so I'm simply just going to use a quadratic formula. That gives me negative 4 plus or minus the square root of 4 squared is 16, minus 4 times 3 times negative 4, all over 2 times 3 is 6, which is negative 4 plus or minus the square root of 4 times 3 is 12, times 4 is 48. Since I have a negative and a negative, that makes it positive. So 16 plus 48 is 64, all over 6. The square root of 64 is 8, all over 6. So this gives me negative 4 minus 8 is negative 12, over 6 is negative 2. And also negative 4 plus 8 is positive 4, divided by 6 is 2/3. So these are my x values for my critical points. I could decide whether they're a maximum or a minimum by placing them on a number line and seeing whether my derivative is positive or negative. So for values smaller than negative 2, I can plug in, let's say, negative 10. I would get 3 times negative 10 squared gives me positive, and that's just simply going to outweigh any of my other terms, because this would give me positive 300 minus 40 minus 4 is clearly positive. For a value such as 0, I could see that I would get negative 4, so a negative value. And again, for values larger than 2/3, again, I could use positive 10. I would see that I have a positive value here. So now I can clearly see that negative 2 is my max, and 2/3 is my minimum. So I know that I have a maximum at negative 2, and I also know that it's intercept. So right here, I'm going to have a maximum like that. I'm also going to have a minimum at x equals to 2/3. So I'll go ahead and make a note of that. I'll have a 2/3, and it should be a minimum. In fact, I'm going to go ahead and find the exact value. The exact value at the point 2/3 would be 2/3 cubed plus 2 times 2/3 squared minus 4 times 2/3 minus 8. That's going to give me 8 over 27 plus 8 over 9 minus 8 over 3 minus 8. Or, and this is where things get a little less fun, here I get 8 plus 24 minus 8 times 9 is 72, all over 27 minus 8. That's going to be 32 minus 72 is negative 40 over 72 minus 8, which is negative 20 over 36, which is negative 10 over 18, or negative 5 over 9 minus 8, which is negative 5 minus 72 over 9, or negative 77 over 9. And I can plot that. So this would be my minimum at 2/3, negative 77 over 9. Okay, lastly, I just need to find my areas of concavity. So to do that, I am going to use my second derivative, which is 6x plus 4, and I need to find where that is equal to 0. So to find where that is equal to 0, I simply move my 4 over to the other side. So I have 6x is equal to negative 4. So x is equal to negative 4 over 6, or negative 2/3. And this would be my single inflection point. I can see if I make a number line for my second derivative. Well, for values like 0, which is larger than negative 2/3, I clearly have a positive value. And for values such as negative 10, well, I get 6 times negative 10 is negative 60, plus 4 is still very negative. So I'm concave down until negative 2/3, and concave up after negative 2/3. So I'm actually just kind of going to estimate about where this inflection point is going to occur. I'm going to say it's going to occur maybe here, because I don't really want to plug in this value of negative 2/3 and get an exact point. Regardless, I now have enough to say, or enough to give a pretty detailed sketch of my graph. I have a minimum at 2/3. I know that it's concave up at 2/3. I know that at negative 2/3, I'm going to switch concavity from concave down to concave up. I've got a y-intercept at negative 8, and an x-intercept at positive 2. Here I should be concave down, a maximum at negative 2, 0, and it's concave down from there. So that is a more detailed sketch of my graph. There's my inflection point. Here is my y-intercept at 0, negative 8, and my x-intercept at 2, 0 as well. Any questions? All right, so in general, when you're finding more detailed graphs, you're going to basically want to give those things. You want to say where the intercepts are, what the maximums and minimums are, all of the local ones and the extreme and the absolute ones, as well as intervals of concavity. You'll also want to mention holes and asymptotes if there are any. All right, now let's get into the fun stuff. Next up, we're going to take a look at some optimization problems. So the idea with optimization problems is calculus lets us find maximums and minimums of functions. So when functions represent something specific, such as area, well, we can find where that area is going to be maximized using calculus. So let's go ahead and do an example of this. A farmer is fencing a rectangular field. He has 100 feet of fence, and he's going to place the field next to a stone wall, so he doesn't need to fence that side. And I want to know what is the area of the largest field that he can make. Well, let's start by drawing ourselves a picture. Here's his field. We know that the area is going to be the length times the width. And we also know that he doesn't need to fence one side. So that means that the perimeter, or the amount of fencing that he's going to need, is L plus W plus L, or 2L plus W. Now, it stands to reason that if he's trying to make the biggest field possible, he's going to use up all of his fencing. So I'm going to say that this 2L plus W should use up all of his fencing. Or in other words, he's using up all of his fencing to make his field. Well, right now, we want to maximize area. And in the past, when we've wanted to maximize a function, we've taken its derivative. The problem in this case is we have two variables. We have L and W, and we don't know how to take the derivative of a function with two variables. So that's where this other function comes into play. With this other function, we can make a substitution. Say I can move the two L's over to the other side, and I see that W is equal to 100 minus 2L, and then I can substitute W out of my area equation. And this gives me an equation of one variable. So now that I have an equation of just one variable, I can take its derivative and solve for the critical points. So taking the derivative of my area equation, I get 100 minus 4L. If I want to find the critical points, I'll set that equal to 0. So 100 is equal to 4L, which means that L is equal to 25. That is our critical point. We want to check and make sure that this is a maximum. So when I plug in a value that is larger than 25, let's say 100, I would get 100 minus 400 is negative. When I plug in 0, I would get a positive value, just 100, and that gets me clearly a maximum. So my area is maximized when L is equal to 25, and since my area is equal to 100 times L minus 2 times L squared, or it's also equal to L times 100 minus 2L, I can see that my area, when maximized, would be equal to 25 times 100 minus 2 times 25, which is equal to 25 times 50, which is 1,250. That would be feet squared. Any questions? What if the extreme is not a maximum? If the extrema is not a maximum, you probably set something up wrong. So go back and check through your process and your setup and make sure you've got all the right setup going on. If you're still getting that it's not a maximum, then maybe the problem is asked very strangely, using numbers that might not work. But in general, if you get an extrema that is not a maximum in a problem like this where you would have to have a maximum, then you probably just set it up wrong. Well, in general, you can assume that, but I don't want to say to do that because there will be instances. Let's say you got more than one critical point for your area. Well, then you would need to check and see, was one of these a maximum, is one of these a minimum, or even, it just depends on what the problem is asking. So in general, I like to double check that it's a maximum, because that would match my intuition of what the problem what I should see in the problem. It's just a way of checking yourself. In problems like these where you only get one critical point, you probably don't really need to check it, but it's good practice. All right. In that case, I've got a couple of practice problems all laid out for you. So go ahead and give these two a try, and I'll give you a few minutes to work through those. Can I help you?
Oh no, I was looking. I was like, is this a caution? I was scared.
Yeah, I mean, it's just basically
For what? SSU? Review? Oh, interesting. I was thinking more like, oh, like caution. Yeah. You don't teach? Yeah, there's one. Here. School. What major? Math. Oh, that's cool. Yeah. I'm taking math. I think engineering. Yeah. Taking math. So, yeah, basically. Yes. I was just looking around and see what's like, oh, that's so like you have the session screen, whatever. From that, yes. Yeah, that's good. That's great. That's great. I'll see you around there. Yeah.
You all good to go, or do you need a minute or two more? All right, let's just go ahead and go over these ones. So our first problem, we have a box and we're making it out of a piece of paper. And really what we can vary is this distance here. I'm going to call it x. So if we hold this into a box, I'm going to try and sketch a picture. Our box would look something kind of like this. And this height here would be x. So we can say that the volume would be the length times the width times the height. We know that the height is x. Now then the length would be this distance right here. I'm actually going to draw that in a different color. The length would be this distance here, which would be our 10 inches minus 1x for this corner, minus the second x for this corner, or 10 minus 2x. And that would actually be the same as this distance here. So our total volume would be x times 10 minus 2x for the length times 10 minus 2x for the width. Now if I distribute all this out, I get x times 100 minus 10 times 2x is 20x, 10 times 2x is another 20x, so minus 40x, plus 4x squared. So my volume is then 100x minus 40x squared plus 4x squared. Okay? So then if I take the derivative of volume, in this case I don't need to substitute anything out because I only have a function of one variable, so I can just go ahead and take the derivative of my volume equation. I get 100 minus 80x plus, oops, that should be minus 40x. So 100 minus 40, oh no, I was right, 40x squared, and that should be a 4x cubed. Apologies. So that should be 100 minus 80x plus 12x squared. And to find my critical points, I would set that equal to 0. Well, now I simply need to try and factor this as best I can. I'm going to go ahead and divide everything by 4. So I get 25 minus 20x plus 3x squared is equal to 0. And again, I don't like factoring, so I'm just going to go ahead and use my quadratic formula. 20 plus or minus the square root of 20 squared is 400, minus 4 times 25 times 3, all over 2 times 25 is 50. This is 20 plus or minus 400. Here I have 4 times 25 is 100, times 3 is 300, so the square root of 400 minus 300 is the square root of 100, which is 10. This is all over 50 still. And this, of course, gives me 10 over 50 is 1/5, and also 30 over 50, which is 3/5. And, oh dear, I flipped this around. This should be over 6, not over 50, because my a value has my x squared term, so that should still be over 6. So that would give me, that would give me 10 over 6, which is 5 over 3, and also 30 over 6, which is just 5. And these are my critical points. Now in this case, I do want to know which one is a maximum and which one is a minimum. So again, I'm going to make a number line. When I plug in 0 into my derivative, I would get 100, so that's positive. When I plug in something in between 5/3 and 5, let's say 2, then I would get 100 minus 160 plus 12 times 4 is 48. That would be 100 minus 160 is negative 60, plus 48 is negative 12, so that's negative. When I plug in something larger than 5, let's say 10, I would get 100 minus 800, but then plus 1200 is positive. So here I see that 5/3 is my maximum, and 5 is my minimum. And this matches with our intuition, because if we cut out side lengths of 5 from our box, well then, we're essentially just cutting out the entire box, and there's nothing left. So that would give us a volume of 0 at 5. Okay, so we know that our maximum volume occurs at x equals to 5/3. So to find our maximum volume, we thought all the sides would be equal as there was an equal amount cut out from each side. You are correct. What I was saying when we had the side length of, or the cut length of 5, the sides are originally 10. So x is the amount we're cutting from one corner. So if we cut 5 from the first corner, we cut 5 from the second corner, well, suddenly we've cut off this whole side. And there's nothing left for that. So that would give us a volume of 0, because we've cut up essentially all of it away. So we're cutting out the same amount on each side. It's just that we're basically cutting out the whole box. These were just the potential critical values of the amounts that we could cut away that would give us our maximum and our minimum. So in this case, we found that if we cut out 5/3 from each corner, that would give us a maximum, and if we cut out 5 from each corner, that would give us a minimum. So I'm saying because 5/3 is the maximum, 5/3 is the amount that I'm going to cut away. Does that clarify things for you? So 10 minus 2x cubed is not the volume equation, because when we fold up our box, we're folding up this side, this part right here, and this part right here. We fold those together, and they would become this height right here. I know it's pretty small here. Let me actually blow that up for you. So these blue parts, when we cut out this corner right there, you can think about us folding them upwards, and then it would show up right there. So you can see that our height is actually the amount we cut away. Yep. Okay. But now we found out the optimal amount to cut away, and that's 5/3 for x. So the last step is just to plug this into our volume equation. And all I did is I replaced my x's with 5/3, and I also combined these two terms because they're identical into a squared term. Now 10 minus 2 times 5 over 3 is 10 minus 10/3, which is 20 over 3. So my final answer is 1,000 divided by 9. And that would be inches squared. Oh, I forgot to square. Never mind. It is not 1,000 over 3 over 9. It should be 5/3 times 20/3 squared, which is 5/3 times 400 over 9, which is 2,000 divided by 27 inches squared. There we go. This one makes sense? All right. Let's take a look at the next practice problem, though. Did you guys get this one? Nope. Do you want a couple more minutes to work through it, or should I just go over it now? All right, I'll just go over it then. So I like to sketch pictures, so I'm going to basically just draw a picture of my cylinder. There, I have a cylinder. I know that my cylinder is going to have a radius, and it is also going to have a height. I'm going to call those R and H. And I know that my volume of my cylinder, which is equal to pi r squared h, should be equal to 20 pi. That is given. Volume of 20 liters. And I am trying to minimize the amount of materials needed, or in other words, minimize the surface area of this cylinder. So the surface area of the cylinder, I'll write it A, is equal to the area of the top circle plus the area of the bottom circle, so that's 2 times pi r squared, plus the area of this outside shape, the outside curve. The area of the outside curve is the diameter of the circle multiplied by the height. You can think about unrolling it into a big rectangle, where this part here is the diameter of the circle, which is 2 pi r, and this height here is just the height of our cylinder. So 2 pi r h, and that is the surface area. Well, I'm trying to minimize surface area, so I need to find the minimum of this equation here. The problem is, right now, I have two variables, r and h, in it, so I need to substitute one of them out. Luckily, I have my volume equation that says that pi r squared h is equal to 20 pi. Because I have just one h in this equation, I'm going to try and substitute h out, so I get, by dividing both sides by pi r squared, 20 pi over pi r squared, which is equal to 20 over r squared. And that is what h is equal to. Well, now if I substitute h out of my area equation, I get the area is 2 pi r squared plus 2 pi r times 20 divided by r squared. And this is equal to 2 pi r squared plus 40 pi divided by r. So then my derivative of my area equation, because I'm trying to find the masses, that means I'm taking the derivative. My derivative of my area equation would be 4 pi r minus 40 pi divided by r squared. And again, I just use the power rule. I can move my r in the denominator up to the numerator with the power of -1. That would get me negative 40 pi r to the -2, which I have right here. And again, to find the critical points, I'm going to set this equal to 0. Well, in order to solve this, I'm going to multiply both sides of this equation by r squared. So I get that 4 pi r cubed minus 40 pi is equal to 0. Again, all I did is I multiplied all this by r squared. Then I can move my 40 pi over to the other side. I can cancel a pi from each side, as well as 4 with this 40 and replace it with a 10. So I'm left with r cubed is equal to 10, which means that r is equal to the cube root of 10. Well, the question asked to find the dimensions, which is both the radius and the height. So I've already found the radius. Now I just need to find the height. Luckily, I know that my height is equal to 20 divided by r squared, which is equal to 20 over the cube root of 10 squared, which we can write as 20 over the cube root of 100. Or we could even write it as 20 over 10 to the 2/3, however you prefer. But these are our final answers. Any questions? All right. Differentials optimization is pretty fun. One of the more fun uses of calculus. All right. There is one last topic for today, and that is antiderivatives, which are a bit different from what you've been doing in this course so far. Antiderivatives, as their name suggests, are the opposite of derivatives. Antiderivatives. You might also hear antiderivatives called integrals, because in a lot of ways they're just the same thing. So let's start with what the definition of an antiderivative is. We say that a function f of x is an antiderivative of some other function f of x if we have that the derivative of our capital F of x is equal to our lowercase f of x. So this notation isn't necessarily the best, but it's the most common. You'll see that capital F is used for the antiderivative of lowercase f. And when we take the derivative of capital F, we should get to our lowercase f. So for example, let's say we had of 1/3 x cubed. Because if we took the derivative of 1/3 x cubed, 1/3 x cubed, you would get 1/3 times 3 is 1, and then we would decrease the power by 1, and we would get x squared. So 1/3 x cubed is an antiderivative of x squared. Similarly, we could even do that 1/3 x cubed plus 1 is an antiderivative of x squared. Because when we take the derivative of it, we still get that 1/3 x cubed has a derivative of x squared. The derivative of 1 is just 0. And we could, in fact, do this with any constant. Because the derivative of any constant is equal to 0. So because of this fact, you'll often see that your most general antiderivative is written f of x plus c, where c represents any constant. Because when we take its derivative, it's just going to go to 0, so it needs to be included in our antiderivative to make sure we're accounting for all the possible antiderivatives, but it's not necessarily going to show up in our derivative itself. Okay. Let's see. You haven't really learned a ton of methods to solve for antiderivatives yet, but right now, the easiest way to do it is maybe think about just what function you could take the derivative of to get something that looks like your current function. So in this case, when I was looking for the antiderivative of x squared, I said, well, to get an x squared term, I would need to take the derivative of an x cubed term. Well, when I take the derivative of x cubed, I get 3x squared. So in order to fix the coefficients and get just an x squared, I can take 1/3 of each of these. So then the derivative of 1/3 x cubed is exactly equal to x squared. So I know that 1/3 x cubed was my antiderivative. So here's a couple of quick practice problems. Go ahead and find the antiderivative. Oops, I don't want to throw those in there. And I'll give you a couple of minutes to work through those. All right, let's go ahead and run over this one really quick. I can remember where I left the pen. There it is. Okay, so first off, if we're looking for the antiderivative of sine x, well, a function we know has a derivative similar to sine x would be cosine x. When we take the derivative of cosine x, we get negative sine x. So all we need to do is fix the coefficient. So when we take the derivative of negative cosine x, that would give us negative negative sine x, so positive sine x. Again, we can add on any constant we want. So our antiderivative would be negative cosine x plus any constant. This next one, well, we know that the derivative of e to the x is e to the x itself. So maybe the antiderivative of e to the x should just be e to the x itself. In this case, we have an e to the 2x, but it should still be part of our antiderivative. When we take the derivative of e to the 2x, we get 2 times e to the 2x. So to fix the coefficients, I'm just going to multiply by 1/2. And again, we can see when we take the derivative of 1/2 e to the 2x, we get 1/2 times 2, which is 1. So 1 times e to the 2x, which is good. And again, we can add on any constant we like. This last one, we can actually break this apart just like we do with derivatives and say, what's the antiderivative of x cubed? And then subtract what we think the antiderivative of x to the 4th is. So the antiderivative of x cubed, again, is going to be 1/4 times x to the 4th. The antiderivative of x to the 4th is 1/5 x to the 5th, and we can add on any constant we want. Now, there are a couple of tricks. I'll just start out with one of the most basic ones for finding antiderivatives. And that is if you're finding the antiderivative of something that looks like this, where n is not equal to -1, well then your antiderivative is going to be 1 over n plus 1 times x to the n plus 1 plus any constant. When n is not equal to 1. And you can see if we take the derivative of this 1 over n plus 1 times x to the n plus 1 plus c, well, we would have 1 over n plus 1 times n plus 1 times x, and we would decrease the power by 1, cancel n plus 1s, and we get x to the n. So this is called your power rule for antiderivatives. And one way you'll often see antiderivatives expressed is through this notation here, where essentially this is an integral symbol, and this is kind of what we use to close off the integral symbol. We'll cover where all of these parts come from later on in the course, but this is some common notation you'll see. And the last thing I really wanted to talk about was just kind of the intuition behind what an integral or an antiderivative is. So derivatives have a really nice geometric meaning. If we have a function, well, our derivative at a point tells us the tangent line at that point. Super nice. Likewise, antiderivatives have a nice geometric meaning. If we want to take an antiderivative between 2 points, and one way we'll see that expressed is using this notation here. So taking the antiderivative starting at one point and ending at another point will actually give us the area between the graph and the x-axis on that interval. I'm just going to write that in right so it stands out. So that's kind of the geometric interpretation of what an antiderivative gives us. A derivative gets us slope, an antiderivative gets us area. So remembering those two things will actually help you a lot in just understanding what problems are asking for and understanding why we do certain things in calculus. But that's all I've got for today. If you've got any other questions, feel free to ask. But if not, have a nice day and thanks for coming.